Try and try, try and try. You'll succeed at last.
Well, good morning everyone, and I'd like to put a big shout out first of all to Zay and say thank you very much for making me feel better and telling me that yesterday's video was not actually the most boring maths video he'd ever watched. So hopefully we can continue on with solving some geometric problems using the triangle law, a bit more vectors today. So, solving geometric problems using the triangle law. Now, the triangle law was what we were talking about yesterday, where where AB as a vector is equal to OB take OA. And I say that now because that's going to lead into, you're going to want to make a little copy of something that's in the book on page 244. This little diagram here, going along with this bit here, talking about if the point P divides the line segment AB in the ratio lambda to then carry on with all of this ratio stuff. What does this mean? AP to PB, AP to PB is equal to lambda to... Right, so let's have a little look and see what that's all talking about. Now, I don't know if you wanted to jot that down and pause it before watching this, or maybe watch this and then go back and make the sketch. So the diagram that I showed you briefly there, and we had an O, we had an A, and we had a B over here as well. And the point is, from A to B, from there to there, is going to be equal to that vector take that vector. And what we were talking about is what then happens if you get something that's on here in a ratio where you've got this part here having one length and this part here having another length. And what it's saying is, if I want to know the vector, the position vector of that point P, I'm going to need to go up there and then down there, which is going to look like OA, and then I'm adding to that the fraction of the overall distance from A to B that this is. Now the fraction of that is going to be, I want to go this far out of the total distance, which is those two added together, times the distance from A to B. And what then that's saying is that's the same as saying distance from O to A plus, and we've got that fraction to be multiplied by OB take OA, because that's another way of calling that whole thing of AB. And we're going to use that now to sort out our first of three examples. So I'm now looking at example 16, which is still on page 244, and I'm going to start by talking about some of the information that's there. So it says that the point divides AB in the ratio 1 to 2, and it refers to the origin. So the diagram in the book starts from the origin, it puts a little vector A on there up to point A, and it puts vector B going somewhere over here like this, going to point capital B. And then what it's saying is if I'm looking at the vector that goes from A, or the line going from A to B, point P is such that it divides the ratio, the line AB in the ratio 1 to 2. So that is 1 part to 2 parts there, and that is P. And then it pops a little line down there. And what it wants to know is what is the position vector of P. So I'm going to try to get to there. In order to do that, I'm going to go to A first. So OP is going to equal OA, which I know I'm going to call A, and then it's going to be 1/3 of the way along, because it's the ratio 1 to 2. That means we've got 3 parts altogether. It's going to be 1/3 of the vector A to B. And we can say, using the triangle law that we learnt yesterday, when I said, oh yes, all you really need to do is count along to go down. Well, that got us into it, but actually we do need to remember it, because in a question like this, we don't know what the coordinates are. We can't just count the squares. So this time we're going to have to say I've got 1/3 of, going from A to B is like doing that from there and then taking the A away. That would get me back to there. So it is OB, which is my B, take OA. Now I'm going to write it in terms of A and B, because that's what we're going to need to be expressing it in. So OA is A, then I'll have 1/3, and in brackets I've got my OB is B, take OA is A, and then all we need to do is expand this bracket, which is going to give me A plus 1/3 B, take 1/3 A. And then we've just got a little simplification to be done at the end. When I take 1/3 A from A, I've got 2/3 A plus 1/3 B. And you can leave your answer like that. Sometimes people like to then factorize it at the end and say that's the same as 1/3 2A plus B. But that's optional unless they ask you to leave it in that specific form in the question. But that can then lead on to solving other things depending on what's going on if it gets trickier. Okay, that's the end of that example. 2 more to go. Now, due to the wonders of modern technology, it might seem to you that no time has gone by since example 16, but actually I've gone and made myself a cup of tea and got myself 2 biscuits, and the reason for that, a fig roll by the way, and a plain chocolate digestive. And the reason I've gone for 2 such big names in the world of biscuits is this example. This is going to take some thinking about to follow it through. You may need to pause the video, rewind it, and watch things more than once on here. But don't give up with it. Don't just let it ride over and then go on, because it is quite an important one. So the question here, it says that OABC is a parallelogram again, and that P is the point where the diagonals of OB and AC intersect. The vectors A and C are equal to OA, so there is OA is A, and OC is C. So those bits are nice and obvious. Now, in order to prove this, we're going to need to think about how we get to P, and we're going to need to do it in slightly more than one way. But first of all, so if we're proving it cuts it in the middle, this must be halfway between A and C and A and B. So we need to think about the vectors for AC and the vectors for OB. Before we go further, just in case you've never noticed, on a parallelogram, the 2 diagonals are not the same length. They do bisect, but they're not the same length. This one here is going to be shorter than this one here, which is going at either end of the long lengths like that. And that is why it's not that simple. But it starts off being quite simple because first of all I need to know how to do OB. And OB, hopefully you can all see, is going up A and then along C there, so we can call that A plus C. And the other thing we need to know is AC. Now AC we can get using the triangle law and say we know that that is going to be OC minus OA. Let's put that in again because it's just worth getting it into our heads so we never ever forget it. So that is OC is C minus OA is negative A. So we know that for OB and we know that for AC. Now P we are hoping is halfway along AC and we're hoping it's halfway along OB, but we can't assume that, so we're going to give a couple of letters, and the two letters we're going to use are lambda for OP. So OP is going to be lambda, a number or a fraction that we're going to multiply by, so OP by the A plus C. That one was quite nice. This one a little bit trickier because to do AC we're going to be using that, so then we know that AC is actually equal to little a, and I'm going to have to define it like this. Sorry, I wasted your time there. I spent all that time thinking about how clear I was going to make it. So reset, we're going from A to C, which means we've got to do the OA and then we've got to do that one there, which was the C minus A. Yeah, so we're adding on C minus A, but we're not going all of C minus A, we're going that fraction of it. And that fraction of it is not going to be the same, well, we're hoping it's going to be the same as that, but we can't assume it, we've got to prove it. So we use a different Greek letter, which is the one that popped up in the last one. And that's got a funny name. I didn't know what the name was, so I've just been off and I've Googled it, and then I was so confused by looking at that I Googled how to pronounce it, and I ended up on Google Translate as well, and that is actually mu. Yeah, I'll say that again, mu. So I don't know, I mean Greeks might pull me up on that, but mu is what we're calling that. So mu, if we just think of it as mu, we'll be fine. So now we've got to those two, we're going to need to have a little look at thinking about how we can combine these. And whenever we do that, I'm hoping that you might be thinking about simultaneous equations. Okay, this is a point at which I should be giving you all a biscuit, but instead I've just eaten one myself. Because as I was saying that, you may have noticed I was slowing down thinking, what's going on there? I've called it AC, haven't I? And I'm hoping that you may have spotted that what I've done there, because I've gone up A and then I've done AC, I've actually done, and then I've done AC, but I was talking about going that fraction to there. This was a different way of doing OP. So what I've done is I've said I'm going up A and then I'm doing A to P, which is a fraction of A to C. So this bit here is a fraction of A to C, that bit there is OA. But they're both giving us our position vector of P from the origin. So what we're saying is that lambda A plus C is going to be equal to A plus mu C take A. And I haven't made that up, folks, I can swear that is actually mu. Right, and now what do we do? Well, we can expand these brackets to give us lambda A plus lambda C is equal to A plus mu c minus mu a. And how are we going to solve this? We're going to solve this because we're going to think about the a's separately to the c's, because if these are going to be equal, this a must be equal to the lambda a is going to be equal to the a there, take that a there, and the lambda c is going to be equal to just the mu c. So this shows here that we've got this featuring and that featuring. Now we've got the a's and the c's, but they're kind of irrelevant. So I can divide, because why are they irrelevant? They're irrelevant because they're in every single term of our equation. So I can divide everything by a, and I get that lambda is equal to 1, because a divided by a is 1, minus mu a divided by a is minus mu. And over here we can divide by c to get rid of the c, and we get lambda is equal to mu. Here we've now got two different equations for lambda which we can solve simultaneously. So if I write this one underneath here, you could also rearrange them and put them in your graphical calculator if you could remember how you're going to do that. But it's quicker actually just to say I've got negative mu there, so if I add them together, the two equations, I get 2 lambda there, and I get negative theta plus theta is 0, so I just get the 1 that was there left, and then I can solve that by dividing by 2, and I get my lambda equaling a half. And if you remember that because of that, that also equals a half. So P is the midpoint of both of them, because on both of them it was a half times what we had for AC, and it was a half times what we had for OB. So we should write that down, shouldn't we? We always need a statement. So P is the midpoint of both diagonals, proving that they bisect each other. And you might think that you deserve to stop there, but we are going to have another example as soon as I've had another bit of biscuit. Right, this is our last example for today then. The fig roll is now a thing of the past, and I'm well into my plain digestive, I can tell you. So here we're given two position vectors, not position vectors, just vectors. Get from A to B, we're moving 3 to the right, and we're going down 2. From A to C, we're going 1 to the right, and we're going down 5. And we need to know the size of the angle BAC, so the angle at A, in degrees. Well, the only way to make sense of this is, as ever, with a drawing. There's no point putting sort of my X and Y axis in there, but I can still think in that way. So I'm going to start from A, because that's what I'm told about here. So here's A, and 3i means 3 to the right. I'm actually just going to pencil that in with a pen, and then down 2. So that's my minus 2. But that just means that length is going to be 2, and that gets me to B. Then A to C is 1 to the right, and then 5 down. 1, 2, 3, 4, 5. So I think I'm going to draw that so that I've got some right angled triangles that don't get in the way of my main triangle. I'm going to draw it like that, so it's going to say 5 there and 1 there. The negative doesn't really matter now. I've got my triangle going round there, and the angle BAC is going to be that one there. And from here to here you can sort of see that that distance there is 2, and that distance there is 3. If you wanted to, and we may as well because it's all good maths, you could work that out using what we know already about vectors, in that BC is going to be AC minus AB. So that means that BC is going to equal AC, which was 1I take 5J, taking away, I'm going to put this in brackets so I don't make a mistake, 3I take 2J. Now when I take 3I away, that's going to give me negative 2I, which is my negative 2 there. And then I've got to be careful, because when I take a negative, I have to add, don't I? So adding 2J to negative 5J gives me negative 3J. So that is how we get there using the triangle law. Now we've got our triangle here, and I've got all of these distances, which means I can use Pythagoras to find the 3 lengths. And when you know 3 lengths and you want to know the angle, then we're looking at the cosine rule. So AC, in fact I'm going to label these sides now, so that is little a, opposite big B you get little b, and opposite capital C you get little c. So we could say that A is going to equal the square root of 3 squared plus 2 squared, which is 9 plus 4 is 13, so that's root 13. We'll leave that like that. Then shunt on down, and we'll do C next, because C looks just the same. It's also 3 along and 2 down, so that's 3 squared plus 2 squared is root 13. So we've got a nice isosceles triangle on our hands, folks. And the last one, B, is going to be 5 squared is 25 plus 1 squared is 1, so 25 plus 1 is 26, root 26. Remember, that doesn't mean that those two are half of that one. Of course, you can't have a triangle where the longest length is exactly double both of the other two, because you'd just have a line. Think about it. Anyway, what was I talking about? Oh yes, we were going to use the cosine rule now that we know these lengths. So when cosine rule for angles, personally I always know the one with the lengths and then I rearrange it, but cosine rule for angles is cos A equals B squared plus C squared, take A squared all over 2BC. All you've got to do then is put into your calculator cos minus 1 and then ramp all of this in here. So we have got B squared will be 26 plus 13, take 13, and we square our root. Oh dear, take 13, that's going to just give us 26 on the top, isn't it? All over 2 times root 13 times root 26. So I'm going to put that all into my calculator now, just like that, and I did the 26 bit on my own, and that gets you 45 degrees. If you look in the book, they do a little bit more stuff to show you that that's actually 1 over root 2, isn't it, when you cancel all that down, if you like. But 45 degrees is our answer, and we are done. So all I need to do now is let you know which questions you need to practice. Okay, so on page 246, exercise 11E, now there's only 6 questions, and it's such a beautiful day, but Boris has told us we're only allowed to go out for a short bit of exercise just with those members of the family or whoever it is that we are living with. So I'm sure you'll want a little bit of maths to practice. So all 6 questions I think would be good to go for. I will be giving you some homework tomorrow for the rest of vectors to sort that out. We'll have one more thing before the Easter break, and then just make sure you you really get into that, and you can always go ahead and have a little look further on in the book if you get bored over the Easter break as well. Okay, that's all from me for today. Bye bye, maths friends.